Imagine stumbling upon a hole nearly 175 meters deep and 1.6 kilometers wide, with a rim rising 46 meters above the surrounding plain. What would you think? European settlers came upon just such a hole in the 19th century in northern Arizona, about 64 kilometers east of Flagstaff. Chunks of meteoritic iron were found scattered over an area about 16 kilometers in diameter around this hole or crater. In 1891, mineralogist A. E. Foote published the first scientific report on the crater after analyzing a sample of native iron sent to him that turned out to be a fragment of a meteorite. Even after collecting and analyzing samples, he didn't make any connection between the fragments and the crater. Since Foote didn't find any evidence of volcanic rock, he was unable to explain the origin of the crater. He concluded that the iron oxide fragments were pieces of a meteorite that had burst before it reached the ground. Later, in 1891, Grove Carl Gilbert, the chief geologist from the United States Geological Survey, heard a presentation by Foote and became interested enough to conduct a scientific study of the crater. Gilbert wanted to test two competing hypotheses of how the crater was formed. Was the crater formed by the impact of a giant meteorite from space, or was it the result of a tremendous volcanic steam explosion? Gilbert assumed that if the crater had been created by an impact, the iron impactor must have been huge, close to the size of the crater. If this were true, he expected that the volume of material ejected from the crater would be far less than the volume of the crater itself. Also, he expected that a large impactor mass would be left buried in the crater floor, and that this metallic mass would be detectable by magnets or compasses. Neither of these expectations was found to be true. Therefore, despite the presence of small iron meteorites and the lack of volcanic rocks found in the surrounding ejective field, Gilbert concluded that the volcanic hypothesis must be correct. In 1901, a successful mining engineer named Daniel Moreau Barringer learned about the presence of small balls of meteoritic iron that were mixed with ejected rocks on the crater rim. Barringer concluded that the crater undoubtedly had been formed by an impact. Barringer, like Gilbert, assumed that an extremely large impactor would have been necessary to create such a large hole. Barringer believed this large iron mass must be buried beneath the crater floor and that it could be mined for a huge profit. Without ever seeing the crater, Barringer and his friend Benjamin Chew Tillman formed the Standard Iron Company in 1903, securing the mining patents for the crater and the land around it. The shape of the crater led them to believe that the meteorite had come down from directly above. Therefore, they began exploratory drilling into the floor of the crater to find the meteorite. In the process, they discovered rocks that had undergone extremely high pressures and had been changed by the shock of the impact. In 1906 and again in 1909, Barringer presented his pro-impact arguments to the Academy of Natural Sciences in Philadelphia. His proof included the presence of millions of tons of finely pulverized silica created under enormous pressure, magnetic iron oxide in the shape of globular shale balls scattered around the rim and surrounding plain, the random mixture of meteoritic material and ejected rocks in a symmetrical distribution around the crater, the deposition of rocks on the rim and surrounding plain in opposite order from the underlying rock beds, as if the beds had been overturned, the absence of volcanic rocks in the vicinity of the crater. In 1907, the eminent geologist George Perkins Merrill visited the crater. In published works, he concluded that previously unknown varieties of metamorphosed sandstone, identified by Barringer as varieties A and B, could only have been formed under pressures far greater than any produced by terrestrial processes. He also raised the possibility that the meteorite had largely vaporized on impact. Not surprisingly, not all were convinced, including Gilbert. During the same time period, astronomers were furiously debating the origin of the craters on the Moon. As with the Arizona crater, most astronomers initially assumed that those craters were volcanic. Gilbert himself, ironically, was one of the first to argue for an impact origin in a paper published in 1893. One objection to the idea of an impact origin for the lunar craters was the fact that most lunar craters are round. Astronomers had calculated that most meteorites would have struck the Moon at oblique angles, producing elongated craters. Barringer had already experimented by firing rifle bullets into rocks and mud, and had discovered that a projectile arriving at an oblique angle would nevertheless make a round hole. In 1928, astronomer F. R. Moulton calculated the amount of energy that would be produced by an impact at the enormous speed typical of a meteorite arriving from space. He concluded that an object big enough to create the crater would probably weigh only 300,000 tons, 3% of the amount estimated by Barringer, and too small to justify any further drilling. In addition, Moulton argued that the explosion caused by the impact would result in the total vaporization of the meteorite. By November of that year, it had become clear that other prominent scientists agreed with Moulton. Within weeks, Barringer died of a heart attack. In 1929, work was halted at the crater. The mining venture that had started with an intuitive leap lasted for 27 years, cost Barringer and his associates over $600,000, which is over $10 million in today's money, and produced nothing. In the process, however, Barringer succeeded in convincing most of the scientific community that his impact theory was correct. Ultimately, astronomers such as A.C. Gifford were able to demonstrate that the force of an impact at astronomical speeds, which are literally faster than a speeding bullet, would result in the destruction of the meteorite, and for most impact angles, the resulting crater would be circular. The recognition of lunar craters as impact craters, which was not fully accepted in the scientific community until the 1960s, was essential for the general acceptance that the Arizona crater was of extraterrestrial origin. Gilbert and Barringer's assumption that the meteorite would have been similar in size to the crater was incorrect. Due to the high energies involved, the impactor responsible for the creation of the crater would have been largely melted and vaporized on impact, leaving only small pieces of evidence, not one large metallic mass. Scientists now believe that the crater was created approximately 50,000 years ago by a nickel-iron meteorite approximately 45 meters across, weighing about 270,000 metric tons, and traveling at a speed up to 20 kilometers per second, or 72,000 kilometers per hour. The explosion created by its impact was equal to 2.5 megatons of TNT, or about 150 times the force of the atomic bomb that destroyed Hiroshima. In 1946, the crater was officially named Meteor Crater. The proper scientific name given by the Meteoritic Society is the Barringer Meteorite Crater. In 1963, geologist Eugene Shoemaker published his landmark paper analyzing the similarities between the Barringer Meteor Crater and craters created by nuclear test explosions in Nevada. Carefully mapping the sequence of layers of the underlying rock and the layers of the ejecta blanket, where those rocks were deposited in reverse order, he demonstrated that the nuclear craters and the Barringer Meteor Crater were structurally similar in nearly all respects. Additionally, working with Ed Chow, Shoemaker discovered the evidence for shock transformation of quartz into coesite and stishovite. His work provided the clinching arguments in favor of an impact origin to the Barringer Meteor Crater, finally convincing the last doubters.